Hello, everyone. Today, we're going to be presenting a Lambda Learner. It's a method to incrementally learn personalization models using streams of data. This is work done and influenced by many teams at LinkedIn, and I'm just presenting the work on their behalf. Uh, Feel free to drop any questions that you have on the chat, or if you want to interrupt me, go ahead and we can make this more conversational. Before I get started, a little bit of an introduction about myself. I've been at LinkedIn since 2015. I've worked on a bunch of problems related to data and machine learning there. Some of them include search and recommendation problems, marketplace matching problems, like expanding the audience and bidding for advertising, as well as optimization algorithms for deep learning. Before LinkedIn, I spent 2 stints at both Carnegie Mellon University as well as Microsoft Research, and I'm excited to give you the presentation today. Although we're going to talk about near real-time personalized models that can apply to any generic recommender system, we're going to ground the application in LinkedIn ads, or sponsored updates as we call it, where the task is to predict the click-through rate of an ad given a LinkedIn member's browsing context. Now, these are ads that you see on your LinkedIn feed, and it could be in any given format. It could be just plain text, it could be a form, a video, or even a carousel, right? So our task is to predict whether a member is going to engage on a given piece of content or not. And so this typically is a very large-scale machine learning problem. What I mean by that is we process about 10 terabytes of data per model. We run about 50 machine learning A/B tests simultaneously. And we use the entire LinkedIn economic graph to mine for features. And this graph is typically about 50 billion edges and 1 billion nodes. And all of the features are extracted from this, and then we train our model. So when I say model, typically a model contains 2 different components, one responsible for the generalization performance, and the other that is responsible for the memorization performance. And any embedding-based models, deep learning models, nonlinear models are good at the generalization piece, right? And the part that's responsible for hyperpersonalization or memorization on entities are typically interaction features or ID-based features. So if you have 500 million members, if you use a unique ID for each member and you learn something that is personalized to that member, you tend to memorize what the member is doing on the site. And so that's what I mean by the memorization aspect. A unique part of this memorization features is they're transient and they're ever-growing. What I mean by transient is an entity that's an entity or a member that's active during my training data is not necessarily going to be active during my test period, right? So they might just go away in a given time window. And they're ever-growing because we keep adding content on LinkedIn, we keep adding new members on LinkedIn, so that space is going to keep growing. And updating this part of the model fast is critical to performance, right? And that is the focus of Lambda Learner. How do we update the memorization part of the model as fast as possible? To understand why it's important to update this model, right? Think about the advertising use case. When a new ad campaign is created, it can reach 1,000 impressions in a few minutes. And if you don't have your model that's already trained, then you're going to be recommending this ad campaign to maybe people that are not interested in this ad anymore. Similarly, if you think about a job posting, right? As soon as I go create the job and submit it and it's live, it could reach millions of job seekers in a very short period of time. So it's important to get your personalization models up and running quickly so that you don't waste people's time in showing them jobs that they're not interested in, or showing jobs to people that might not be qualified for a certain job. So in both cases, recommendation models need to learn from data as quickly as possible. And Lambda Learner helps you do that. At LinkedIn, we use an ensemble called GAME to predict this click-through rate and personalization models, where we have one global model that could be a tree model, it could be a deep model, or whatever model it is that you like. But we boost that global model with a per user model or a per item model. And so we have a large number of these small models called the per user models or the per item models, and we have one large global model. Now, having these different models give you different levels of granularity and different levels of tuning to eventually improve the performance of the entire ensemble. These per entity models are called random effect models. And they're typically very, very small. Think linear models, but and they're trained on the residual of the global model score. And the best part of training these random effect models is they only depend on the data corresponding to that entity. So if I have 100 million members, I can train each member's model just on their data. So it's really, really like small data learning and not huge amounts of data. Now, I described that we are going to train these random effect models, and um, we need to train them fast. But what does it look like to train them fast, right? What are the challenges? So frequently training these large number of linear models, the data size can get larger and larger with time because each random effect is going to add more data with time. But the model training is inherently parallelizable. What I mean by that is we can train all the 100 million models in parallel, and model updates can be asynchronous, which means if you have an advertiser that has a huge volume of data, you're going to kick off training for them multiple times before you kick off training for an advertiser that has very little data, right? So those are the constraints under which we're going to train these random effect models. Now, to do this, we are going to not use the typical batch loss that we're used to. We're going to change the loss function to create something called the time discounted cumulative loss. And the reason we want to do that is we have only access to data at a certain mini batch because we are dealing with streams of data. We take a snapshot of, at time, we get some amount of data in time t plus delta t, and we're going to use that data to train a model. So the small f sub t is the loss at mini batch t, and the capital F sub t is the overall training loss. So if you notice, we are aggregating these mini batch losses across time. Each time we're discounting it by a factor delta, and we get the overall loss function. Now, when delta is less than 1, it's a time discount. And what that means is I'm saying, hey, the older the data, the less important it is to the loss function. Or another way to say it is the more recent data is going to influence the loss function more. So this way, if there is a current event or if there is some new change in the ecosystem, you want that to be captured as soon as possible. Now, a big problem with the current formulation is that the loss function depends, if you notice, the loss function still depends on all of the data from time 0 all the way until time t, which means I need to hold all of that data in memory to be able to train over this loss function. To work around this, what we do is we introduce a Gaussian prior over the model parameters. Let's call that P of beta. And because our loss function is a log logistic, and we will also get a Gaussian posterior. And now we rewrite the loss to include the prior term. Now, this doesn't solve anything. We still have a loss function that depends on all of the data. So now we introduce a quadratic approximation on the capital F sub t minus 1. So this way, we're saying that, hey, the loss doesn't depend on all of the data anymore. The loss only depends on the solution that I have until time t minus 1. And we introduce a quadratic approximation that says the new solution is going to be very close to the old solution. And we then depend only on the term ft, or the loss at time step t. And so this is our new loss function, and this is what we're going to try to optimize. Now, what this means in a Bayesian context is this is equivalent to using the posterior at time t minus 1 as the prior to compute the solution to time t. And this way we get rid of all our dependence on the previous data. Now, since we have the posterior covariance also in the output, instead of using just a simple scoring of the coefficients, we could sample from the solution using Thompson sampling. And now our entire system behaves like an online contextual bandit. So that's another use case for this. Apart from the typical recommender system application, you could also use this as a multi-arm bandit with a really fast feedback loop. So I described the motivation, the problem, and the theoretical framework to solve it, right? But what does it take to build this in practice? Now, we deploy this incremental learning in production with the expectation that it's going to make improvements on multiple fronts, right? We ideally want to reduce the cold start delay. What that means is with incremental training, we're able to deploy random effect models learned on newly observed entities with very little data. In the context of advertising, this includes new advertisers, newly published advertisements, as well as new LinkedIn members. So we're able to personalize really fast when these new entities enter the ecosystem. And the same applies to returning entities that may have been dormant for a very, very long time. As soon as they become active, we want to personalize for any actions that they might take on the platform. The second thing we want to do is we want to respond better to data shifts. What is a data shift? A data shift is introduced when new patterns are introduced for specific entities. An entity is again a member or an ad or a job or whatever it is, right? Now, these shifts can be either external to LinkedIn or it could be internal to LinkedIn. An example of an external event, it could be current events, it could be the news breaking out, it could be some disasters, anything that changes outside LinkedIn's ecosystem. Our recommender systems still need to evolve to accommodate for changes in interest. But you could also have internal changes, right? You could have a member move from San Francisco to India, and then their job recommendation should suddenly change, right? Now, if they relocate, you have a lot of time to make these changes. But what if they're just traveling from one place to another? So you need to respond to these data shifts as fast as possible. So to address these problems within the advertising ecosystem, we built out this nearline infrastructure. Our nearline infrastructure is dependent on three major components, which are built on a variety of technologies, many of which are open sourced. The first is the streaming data processor. Now, this contains a combination of Apache Kafka, which is a distributed messaging system, as well as Apache Samza, which is a stream processing system. The streaming data processor is responsible for gathering tracking data both from our front-end and back-end sources and passing this data from one component to the next. We also rely on a scalable key value store. Now, this is responsible for maintaining a shared state of our random effect models, and it's also critical for asynchronous updating and offline recalibration of our models. And I briefly mentioned that we have some global models, right? Now, these models, they could be trained on Apache Spark. They could be trained on XGBoost if you're using a boosted decision tree, or you could use TensorFlow or PyTorch if you're using a deep model as your global model. But the important point here is your global model is agnostic to what Lambda Learner is going to do. Let's dive a little deeper into our first component, which is the streaming data processor, right? So the arrow shows that this component is responsible. Once you take a look at LinkedIn and you're viewing the app, the streaming data processor is responsible for getting all of your raw data to your first streaming processor. Now, the goal of incremental learning is to reduce the gap between a member's action and the updated model. One of the largest bottlenecks in this process is the production of training data. In order to address this, we emit all feature values used to make predictions in real time from our service. And we use Apache Kafka to do this. Now, this enables us to skip very large offline joins, and it also allows us to capture the correct feature states for all our predictions. So there's no feature collection stage later. Everything happens as you view a certain impression or an ad or a job on the site. We then leverage Apache Samza to produce streaming joins between the features that were tracked, as well as the front-end interaction topics. So if you click on something, you dismiss something, you dislike something, all of these are emitted to different topic streams. And Apache Samza does a streaming join against the features and the labels. In practice, one of the biggest challenges with streaming joins is you have windows of data, but you have to decide how long am I going to wait on this window to decide whether an event was a positive or it was a negative and the member just completely ignored this item. And in practice, this is just a heuristic. It's a heuristic between availability and recall. If you wait too long, you're going to slow down the data processing, but you're going to be creating really high quality data with 100% of your label coverage. But if you wait too short, You're going to produce data in increments of every minute or every 2 minutes, but you're going to miss a large chunk of the positive labels. So what we do is we find how long should we wait to capture 95% of our labels or 99% of our labels, and then close the window at that point in time. After performing this join, we again use Kafka to publish the output. Now, this time the output is a complete training example. You can think of this output as it has all the features, it has all the labels, it has everything you need to start training your model. So you might notice that we keep using Kafka in and out of every topic, of every streaming job. And that's a common pattern across this entire work. Now, so far we have produced features, we've gotten labels, but we're still missing one piece, right? I said that the game models are boosted on the global model, but we don't have global model scores. So the next step is we have a streaming processing component that consumes training data and produces the exact same data with just one additional score, which is the global model score of the training data. Now, you might ask, why, if we are tracking all of the features real time, why don't we just track the global model score also real time? Now, you could do this, but it's not going to be as accurate. And the reason for that is at LinkedIn, we're running a lot of A/B tests. And so every request typically has only one global model's score that is being logged. But for training, you want all the global model scores to be available. And this is why on a separate streaming job, we just go across all of the global models that are running in production, compute their score on the training data, and then log them in the new data. This just guarantees uniformity across our training data set. Now, lastly, we have a streaming processor that does this online learning or Lambda learning. And here there is a very important concept. The Lambda learning happens on a per entity basis, which means when I'm training the online model for one advertiser, I don't need to look at the data from another advertiser. So the first step in this process is it creates these keyed windows where it keys by the advertiser's ID or any random effect ID. It groups by a certain ID and just collects data, all of the training data for a given advertiser or a given random effect key. Now, when it has enough data, right, you could decide how you want to close the window. You could say that, hey, if the advertiser gets 100 data points, start the training. Or you could say, wait for 30 minutes. It doesn't matter how much data you get in 30 minutes. In 30 minutes, you close the window and you start training. Or you could set heuristics based on the variance of the coefficient and say that if the variance increases a certain amount or decreases a certain amount, start training. And you could use any combination of these to close the windows and start training. Most of this is written as Apache Beam processors, and it allows us to train these large number of models asynchronously and parallelly. Now, it's important that it is asynchronous because different advertisers can have different loads coming in. And as you notice in the diagram, when we close the window, what we do is we go to the coefficient store, read the coefficients from the last time step, take the update that I described early on in the presentation, and then write back the coefficients to the same store. So that coefficient store is responsible for maintaining state across the entire ecosystem. And it's also the same store that is used in our online service to serve traffic. So the online service does not know that these coefficients were updated by the streaming job or it was updated by the offline job. All of that is completely hidden away from the serving layer. Now that completes the entire loop, right? So one thing that you might have noticed is from the time you viewed a certain update on LinkedIn to the time the model was updated, we never left the streaming ecosystem. We did not ETL, we did not go and do Hadoop jobs, we did not do batch jobs. So we can close this loop really, really fast. And the only thing that matters is how long do you want to keep these windows open? And that's just a trade-off between availability and recall. Now, there are a few considerations to keep in mind. Because we introduced an approximation, right, that quadratic approximation that I spoke about, there is a chance that your model might degrade over time. And that is application specific. So for your application, if you notice that the performance degrades over time, you could also mix in offline batch updates once a day, once a week or whatever it is, however frequently you think the performance is going to drop. But the architecture is designed in a way that the online system, the nearline system, won't know that there is an offline update that's coming in because they're all writing to the same coefficient store. The second consideration is the time discount factor. There's a delta that I mentioned in the loss function, but I never mentioned how do you fix this delta, how do you update this delta. In practice, this is a function of the domain that you're working on, and we built an offline replay. So we take about 2 weeks of data, replay it offline with different values of delta, and see, hey, how does this model performance degrade with time for different values of delta? So it's just a hyperparameter. And we saw that Lambda Learner is pretty agnostic and doesn't need to be tuned more than once for a given application. So now you know how all of the approximations we introduced to train the model and all the infrastructure that went into creating this in production. What do the results look like in practice, and how does this compare against what we had in production before? So we used 2 weeks of ads data to train the model, and we use a moving window to simulate the online stream, right? So what I mean by that is we don't fix the data and just run algorithm 1 versus 2 and report results, but we use a moving window because when you have a streaming algorithm, you need to take into account the fact that it has more data than an offline batch model. So how do you account for this in reporting? We use AUC as our offline evaluation metric, and we compared Lambda Learner along 2 different dimensions. Along the batch increment size, which is how much data is it going to be using to train each model, and what is the cost of offline training, right? If I use a very complex model, it's going to take 3 days to train. Sure, it's going to do better, but for those 3 days, it has a stale model, right? So we are going to account for these 2 different parameters when we evaluate Lambda Learner. Now, so what are our different options, right, to compare Lambda Learner against? We compare it against 3 batch variants that differ in what data is available to them, and it's all visualized in this diagram. Now, left to right is time. The leftmost data segment here is available to all the variants. You can think of each of these lines showing different segments of data. Left is the oldest data, right is the newest data, and the left data is available to all of the models. In Lambda Learner's case, this data is used to train the prior model. And the rightmost data is used for evaluating all of those models, and that's the evaluation period. The middle segment is where all the models differ. The first model, which is the batch model, is not updated at all. So the middle segment has no data that is updating the model. The second one is a realistic batch example, which is updated periodically, but there's a training cost associated. And that is visualized by the gap there. And the training cost just means that if I start training the model at 10 a.m., I can use data that ends at 10 a.m. But if I take 4 hours to train, the time from 10 a.m. to 2 p.m. is not used in training, and at 2 p.m. I'm going to start serving, right? So that 10 a.m. to 2 p.m. is the gap or the training cost. The third variant, which is a 0 training cost, is a theoretical upper bound. We can never realize this in practice. What this is trying to say is if you start training at 10 a.m., you have completed training also at 10 a.m., and you can start serving data at 10 a.m. This is just for us to know how much of opportunity are we leaving on the table with Lambda Learner. And the last variant is Lambda Learner, which has access to the same data as your upper bound. But now the training cost is actually very close to 0 because training Lambda Learner is not expensive and negligible and can be done asynchronously. Now, this plot shows how the performance of the models change with time. The batch model is not updated and degrades, but Lambda Learner's performance is stable. Actually, this is a really surprising result because Lambda Learner uses an approximation of the oldest data with the Gaussian trial. And we expected that the error associated with this approximation would accumulate over time and degrade the performance, but it does not happen in practice. And this is a very encouraging result for us. Now let us look at the performance of our method and compare it to different batch baselines for different update frequencies and costs required to update. There's nothing surprising that the way the batch updates behave on this plot as update frequency decreases left to right, the performance of the batch updates consistently degrade. Also, the batch updates with lower training costs perform better. You can see that the curves nicely stack on each other, which means that lower the training cost, the generalization performance is going to be better. So we have motivation to decrease the training cost as much as possible. Lambda learner is the solid green line, and it outperforms all the batch variants except for the theoretical upper bound. And even in that case, it gets really close as the update interval increases. Now, in practice, that update interval for us was 6 hours, and that was our baseline that we were competing against. So in the real production system, Lambda Learner outperformed this batch model, especially improving performance in both revenue and engagement on newer advertisers, which was our original goal. But apart from this improvement in personalization and modeling, there were infrastructure wins. First, we think that the new data collection process is more reliable because it uses fewer processing steps, reduces the likelihood of engineering mistakes, and cleaner data. Second, of all the data collection processes, this approach that we took was more efficient in terms of large offline joins or ETL processes. So it was 20 times faster, and it reduced the data availability from taking 10 hours before to just a few minutes. Finally, because of getting rid of these large offline joins, it was less expensive from a cost to serve perspective. It was almost 5 times cheaper to build out this than relying on large offline joins and similar things. So that's pretty much the summary of our work. Thank you everyone for attending. And please reach out with any questions that you might have. There is a more detailed version of this presentation that we submitted to KDD, and the paper is available on archive. We have also open sourced this, and we have our GitHub link on the slide as well. So if people have any questions, you can leave it on the chat. You could ask it here. We could also have an open discussion. Why do I need to predict CTR? So that's a good question. So in any recommender system, right, you have a lot of content and you have a lot of members. How do you decide which content you're going to show to which member? This is the typical Netflix problem, right? When you log into Netflix, why do you get shown certain videos? It's because Netflix under the hood has a CTR model, and it's trying to predict what kind of video is Adrian most likely to engage with. Make money, yes, but also engagement matters, right? If we don't show you engaging content, you're going to leave the platform at some point. Also, when you're applying for jobs, if I don't, relevance. If I don't show you the right kind of jobs, then you're going to think that LinkedIn sucks. They don't show me the right kind of jobs. Or you're going to think that I keep applying to these jobs, nobody ever responds to me. So we're trying to strike that fine balance between what you're qualified for and what is engaging to you. Thanks for the question. Yes, so there's definitely an economic graph research team. I think you should look up LinkedIn and economic graph research. We do have collaboration with academia and researchers on how to get access to the data that we have, as well as work on problems that we care about, especially with providing economic opportunity to everyone. Reach out to me offline or reach out to me on LinkedIn. I'll help you get connected to someone at LinkedIn. Any other questions? Anyone else? If not, this was a really fun presentation for me to put together. I hope everyone enjoyed it, learned something. Please reach out to me offline on LinkedIn. And thank you.